radio telemetry. And we'll explain these as we go along. An ESD can be initiated, as I said, by any out-of-range operating parameter, and this results in a controlled shutdown, placing in safe mode. This would be the most common type of ESD of the ESDs that are generated. As I mentioned, very rarely have I seen an actual emergency condition, what would be considered an emergency situation, that would generate an emergency shutdown. Fire being one of those examples, a true emergency situation. An ESD should and will be initiated by the following emergencies. Again, we use this term, in a very, very loose manner, but emergencies are one thing, out of operating parameters are another. This slide indicates the relationship between the terminal and the vessel. Both sides, the ship and the terminal, can manually trip the system, and that's called an operator trip. That's if the operator observes something of important nature. Besides, the safest thing to do may be to shut the entire system down and press the what we always refer to big red button. So big red button is hit by the operator on either side. The ship operation, as well as the entire terminal supply operation to the ship, or the bunkering supply operation to the ship, is shut down. And that's the manual trip. You also have what are referred to as automatic trips. And the ship will automatically shut down if it receives a shutdown signal ashore. It's important to note that if a shutdown is going to occur, there's going to be, in 99 out of 100 instances, there will be communication between the ship and the shore prior to a shutdown. I've never experienced a shutdown that was initiated by the terminal, intentionally initiated by the terminal, where there was not radio communication or telephone communication beforehand. And as you noted, I said a shutdown that was, it's discussed. I have received shutdowns that were generated because of fault within the ESD system, and those are unannounced. I mean, there's no talking about it. All of a sudden, the shutdown occurs, and sometimes that's some type of anomaly within the system itself. But if there is going to be a shutdown because of a situation either on board the ship or within the terminal, in almost every case, there's going to be some type of communication beforehand. I would call the terminal and say, "Hey, look, I've got a pressure problem on board the ship, or I've got a pump that's giving me a problem." There's going to be some type of verbal communication prior to, and so that there's an advance warning giving. If there's an overfilling of a cargo tank on board the ship, or shoreside with a tank that's involved in the actual operation, this can also generate a shutdown. And if it's generated by the shore, it's going to shut the ship down as well. A power loss to your control valves, be that hydraulic power, control air power, things of that nature. If those systems are not functioning, a shutdown is going to be the result of it. If we lose control air is air that is very, very clean and very, very dry. In the manufacture of that air, if you will, or the treatment of that air, it's important that any valves that are controlled by air, the air be very clean and very dry. So there's a separate system for any air that goes to control valves or any control system on either the ship or the terminal. So if this air source is lost for some reason or another, you have now eliminated the ability to operate your valves, any air-controlled valve or air-controlled system. So the system says, okay, I don't have any air, so we're going to shut down, and it shuts it down. Also, an ESD valve moving from full open for some reason. Let's say there's some type of defect within the valve for some reason. And if a valve moves from a full open position on its own, shutdown is going to generate an automatic trip. If there's a logic failure within the emergency shutdown system, the system is always self-monitoring, self-testing while in operation. So if there's some type of a failure within the ESD system itself, this will also generate the shutdown. Fire in the cargo control area is another issue, of course. If there's any type of a fire, a shutdown is going to be generated, as well as the loss of electrical power, either the plant or the ship. An ESD is going to be the result of that. On the terminal side, automatic trips would be a shutdown signal from the ship, overfilling of a receiving tank on board the ship. If there's you've reached that high level alarm on board the ship and the ship shuts down, that's going to generate a shutdown on the terminal side as well. Again, power loss to arm maneuvering, a critical component of the cargo transfer system. A shutdown would be generated. The SD logic failure, power loss to the emergency release system. We haven't covered the emergency release system yet. We will in one of the segments this morning. We're going to take a look at that. But if there's a loss of power to the emergency release system loading arms, a shutdown is going to be generated. So as you can see, anything that is going to impact the cargo transfer operation or the immediate safety of the vessel within the operating envelope of the loading arms, anything of this nature, anything that's an anomaly, that type, a shutdown is going to be generated, and recovery from that shutdown will not be accomplished until the out of parameter situation has been corrected. Important to remember that you do get a shutdown, situation has to be corrected before the system can be reset and brought back online. And that's done in a very, very methodical step-by-step procedure. Any ship movement prior to the emergency release system being activated, that also can generate a shutdown. And the activation of the emergency release couplings, yes, we're going to have a shutdown. When you see how these couplings work, you'll understand why you would have this type of shutdown. And a high level in a surge drum. Surge drum is a safety space, if you will, with on the terminal side, so that the system's protect in case of pressure surge or a quantity surge for some reason occurs. Keep pressures within limits of the system. So if there's a problem in that surge drum, or if the level of liquid in that surge drum exceeds a certain point, shutdown would be generated. So you can see that you have this interaction here. I compared it to a marriage, and you can see how closely the ship and the terminal work. They work in tandem. In the cargo transfer operation, they will work in tandem as well during a bunker transfer operation as well. So for all intents and purposes, they become a single unit. Problem on one side automatically going to be the problem on the other side. Do have this interaction, and it's designed that way, and its system works very, very well. The ESD should initiate the following immediate actions. On board the ship sends out the shutdown signal to shore. Get the shutdown on shore. Vice versa, on terminal, if the signal ship sent is ship shore link ESD system. Trips of the ship's cargo and spray pumps is going to trip your loading pumps on shore. It's going to open spill back valves or kickback valves on the shore side. These are valves that are automatically activated in the case of a emergency shutdown, and they're designed into the system so that any pressure surges are totally eliminated. Trip of a booster of any type of booster pumps on LPG carriers, they will also interact with the terminal side, create a shutdown with ESD valves. The ESD system also covers the vapor return system. When an LNG carrier is in a terminal loading LNG, it is sending vapor, putting liquid into the tank, creating, then you're also displacing vapor in that tank from the ship to the shore. And this transfer of vapor is done with a compressor unit and an ESD. You're also going to stop any transfer of vapor as well as the transfer of liquid. So you can see this relationship. It's a very, very close relationship, and everything is done in tandem. The ESD system links are historically they're well established. There's several companies that manufacture these things. There are some that are more commonly found than others. But the basic design of the system is are similar, and most of these systems work with each other. It's very, very rare to find a system that is not consistent with the standards. The interrelationship between systems is basically regulated, if you will. Systems all have to be capable of working with each other, and recommended that ship and shore system link. We'll touch on that in the next section. I believe different, link, non-link system. But briefly, a link system is that gives you that relationship, that marriage relationship, ship and shore, where they're acting as one unit. In an unlinked system, the ship has the capability of generating a shutdown, but the instantaneous capability is not there, and you can wind up with time delays, and which could be problematic. So a link system is the most commonly used system, and this is probably in all likelihood going to be carried out when we're talking about bunkering operations as well. I personally believe it's the safest system and the most, if you will, foolproof. It's important that they do the link. I certainly recommend that. The ESD system, once again, we're placing everything into safe mode, and it also can play a part if there happens to be an LNG fire. By shutting everything down, you've now reduced the potential source of fuel for a fire. You need to know the watts and the hows to gain an effective advantage in any situation. So the ESD system not only tells you, okay, that you shut this down, but it also tells you why the system is shut down too, and that's very, very critical. There's thousands of monitoring points within the emergency shutdown system. So if you had a shutdown, which one of these, which particular item was it that generated the shutdown? So it's very important to know why the shutdown occurred, and the ESD system is so designed that it will indicate to the operator where the shutdown was generated from and what particular system it was that created the shutdown. And it's important that all parties know the similarities between the vessel and the terminal ESDs. Going into a new port or a new terminal or a new operation, this would be part of the pre-transfer meeting, asking any questions that the operators may have about the shutdown system on board the ship or the terminal. This information can be discussed and exchanged. One more item that takes that's on the agenda when we have these pre-transfer meetings. Ready? Three 16. Another system that works in tandem and closely with and part of the emergency shutdown system is emergency coupling. The emergency release system, we're going to discuss what they for and what they do, the different types. We're going to see a different type arrangement for bunkering operations where hoses are used. And then we're going to take a look at the type of system that is used on board ships for loading arms, and also the system that's used on a ship-to-ship transfer where hoses are used. The use of hoses in a ship-to-ship transfer, the emergency release system is sometimes different than that found in a bunkering system. Hoses are used. So we do have various type systems out there, and it's important that we understand the differences and similarities. The main similarity is we want to have the ability to disconnect from the transfer system operation should there be some unexpected and sudden movement of the vessel in such a manner that it could potentially create undue stresses on loading arms and hoses, causing a breach or a break of the arms or hoses. This equipment is extremely expensive, and unfortunately, the advent of emergency release systems are a consequence of incidents of this type, where a vessel has unexpectedly moved and arms have been torn down, and we're talking millions of dollars or millions of euros for a replacement repair of loading arms, and never mind the downtime of the terminal when one of these events occurred. And as I said, they have occurred early on in the LNG trade. So in order to prevent any potential damage, these systems were devised and installed, and they're found on a worldwide basis now. The emergency release system provides this for safe disconnection of loading arms in the event of excessive vessel movement alongside a berth. For non-mariners, you might say, well, gee whiz, how can this possibly happen? There have been several incidents where an engine has been allowed to go into a underway mode, and steam's been admitted into a turbine, and all of a sudden the propeller starts turning. And one occurrence that happened. A second possibility that we talked about in an earlier segment was a vessel passing close by within a channel at a terminal or in a port. the dynamics of the water being pushed and the effect that it has on a vessel in a berth can cause a vessel to surge off of the berth. And if the surge is of such a nature where it exceeds the limits of the arm can be damaged, so the emergency system prevents this type of incident from occurring. And if there's some other type of an emergency, for instance, let's say some type of a casualty at a terminal or in a bunkering operation that necessitated the departure of the receiving vessel from the berth in a rapid manner. Regulations require that an LNG carrier be capable of departing a berth 30 minutes. Very, very short period of time when you're talking movement of the vessel berth. So the vessel has to be ready to get underway at all times. Emergency vessel that more of a time advantage if something happens. So that you very, very quickly connect, get the vessel out of harm's way. It may be the desire of the terminal, if there's a major incident within a terminal, to get the vessel out of there. So these systems add that safety factor. The ERS is a special connection, and it's fitted to the normal means of a loading arm connection. Your normal means of connecting a loading arm to a manifold or a hose to a manifold is a bolted flange. Depending upon the diameter of the flange, that will ascertain the number of bolts that are used. The larger the flange, the more bolts. You also have quick connect, quick disconnect valves, which are also commonly referred to as ham locks, the hydraulically operated or mechanically operated locking device that grasps the face of the flange and pulls the hose or the arm and the ship's manifold flange together in a tight fit. The system incorporates instrumentation to monitor the ship's position. The emergency release system is a system. It's independent of the ESD system in the sense that the monitoring is done by a separate logic cabinet, a separate electrical cabinet, etc. And but it's integrated with the ESD system, so that if there's any type of movement that exceeds certain parameters, an emergency shutdown is going to be generated prior to any automatic disconnection of the emergency release system. So these two systems work closely together, but they are two separate systems. The emergency release system at terminals. An alarm, you have stage 1 or ESD1. These parameters are preset within the system. There's an operating envelope for the loading arm, and we'll have a graphic as we move along here, and you'll see. The first limits are called stage 1 or our ESD1. What this is going to generate an alarm from the predetermined limit. At this point, a safe shutdown of the cargo system may be activated by the ESD system. The operator may will receive the alarm. There's going to be some type of communication between the ship and the terminal. They're going to say, hey, look, we've got some movement here. What's going on? They will go and investigate. The ship will investigate. The terminal will investigate. If it's deemed necessary, that the safest thing to do may be to shut this down. In this particular case, the operator would generate the shutdown and say, hey, look, we've got a situation here that might take a few minutes to correct. It's the safest thing to shut down. They agree upon this, and the shutdown would be manually operated. If the vessel is moving within this envelope, and sometimes this can occur very, very quickly, You might not have time to go and investigate what the first alarm, and the second predetermined limit is reached. What will happen is a stage 2 or ESD type 2 would be generated. That's a second alarm is sounded. It's different than the initial alarm. And when that happens, the ESD is automatically generated and the arm disconnection automatically commences. Once that has commenced, you are stuck with it. You're not going to reverse this. Once the alarm has been activated and the system has been activated, it's going to follow through to its natural end, which is the actual disconnection of the arms. I personally have never witnessed an ESD2 situation. I believe there is a video on YouTube of an accidental release and what subsequently follows. It's a very smooth operation. Again, I've seen demonstrations of it, full conditions, but it's a situation that takes a considerable amount of time to recover from. So if one of these incidents does occur, that vessel is going to be in port several hours longer than they had intended on being there. The transfer operation is going to take longer than initially planned, and this also can cause scheduling problems within the terminal when one of these events occurs. Once again, this type of event is very, very rare, but the system is designed so that the vessel and the terminal are always protected. The emergency release system is fitted on the lower extremity of the loading arm, and it consists of a flange coupling that's locked hydraulically, and that flange coupling is flanked very, very closely by two valves, two ball valves, or two butterfly valves adjacent to the actual couple. Those valves are close as possible to the coupling because you want to minimize any amount of LNG spillage when the coupling is released. You are going to get a release of LNG into the environment when one of these systems is activated. It's inevitable, but the systems are so designed that the amount of release is going to be minimized. All right. This is a graphic, a very simple graphic of the operating envelope with the predetermined points. The inner area here in the box, this is the area in which the vessel is safe to move. It's not a very, very large area. This perhaps might be maybe 1 or 2 meters either fore or aft of the center line, the arm. So it's a relatively small amount of distance when you compare it to the size of the vessel. So you have a forward and aft window that you can work in, and you also have a lateral distance that the vessel can come off the berth for before an alarm is sounded. And in this particular case, as long as within this operating envelope, this situation is steady state, and there's no issues. Once it reaches a predetermined point outside of this, at the edge of this envelope, this is where you would generate this the first alarm, the ESD1, alerting the operator that there has been some excessive movement and it has to be investigated. Eventually, you can reach this outer point, the arm max operating envelope, and you're now at that point where you're not only going to generate a second alarm, but you're going to generate an emergency shutdown, stopping the flow of LNG, stopping the flow of vapor, and you are going to initiate the activation of the emergency release valves. Those two ball valves will automatically close. Once those valves are closed, the coupling is released, and the connection between the vessel and the arm is now broken. And hopefully it doesn't go any further than that if it does occur. But if it does, there will be no damage to the loading arm. There will be no damage done to the ship. This is a graphic of a typical loading arm. This is the lower extremity of the arm. Flange face. This face is connected to the vessel. The hard connection is made between the loading arm and the vessel. We go back in the flow direction. This is the emergency release coupler right here. This is a flange connection, and this is a locking device. It's a hydraulic locking device that keeps that flange together. On the upstream side of the upstream and downstream side of that is a ball valve or a butterfly valve. These are the actuators here for those valves. So if this emergency release system is activated, what occurs is hydraulic rams close the valve here. This valve closes. They close in tandem. They close together. And once those valves are closed, this hydraulic coupling will unlock, and the break between the break in the arm will occur right here. This section of the loading arm will remain connected to the ship, and this section of the arm will let the loading arm fall backwards. There's a counterweight on the arm, very, very large devices, and there's a counterweight on it. So once this connection is broken, this section of the arm will raise, drawn back away from the ship. So no potential damage done to the arm or to the ship. I think you can visualize. Okay. Now you've got these this section. These arms are connected to the ship. This is free. You're going to have to put all of this back together. So I think you can appreciate that this is going to be a rather lengthy process to reconnect all of this apparatus here. For informational purposes, there's a bypass on here where you just there's a locking device where you disconnect on this actual coupling, and in most terminals the perk valves are tested. Can test these valves without releasing the coupling. So we do have the means to actually conduct the test. Some terminals will actually test these during the emergency shutdown test. Not necessarily every time, but it is done on a regular testing basis, just to make sure that these valves close. And if you're testing them, you really don't want to do release, so you disconnect the releasing mechanism. But we do have the capability of running tests on. On activation, this is the timeline, if you will, if the system is in fact activated. The two valves are closed, and they close within about 5 seconds. You can appreciate that it is done very, very quickly. When the valves are closed, the release coupling tripped. The arm swings by counterbalance, and it was automatically driven clear of the ship, and the outer valve, the loading arm and valve, remains attached to the ship's manifold. So that's the operation of the perk valve, powered emergency coupling. In a hose arrangement, we have something that's going to be a little bit different. Okay, I'm going to back up. The operation I'm currently involved with, we do ship-to-ship transfers, and we use hoses. In our particular operation, we do have a specially designed emergency release coupling valve. It's a valve arrangement. It's driven hydraulically, and it's activated by a physical connection between two ships. And it's very similar in its function and application to the emergency release coupling that you find on loading arms. What we're finding in bunkering operations, and particularly bunkering operations, tanker trucks used, we don't have this powered emergency coupling, but what has been used in place of is what's called a breakaway coupling. Did touch upon this briefly in one of the earlier sections. We had a picture of a breakaway coupling. It's a designed weak point in the system. The bolts have a breaking stress. It's a flange connection. The bolts have a breaking stress less than that of the stress that would be required to break the hose, so that if an undue force is placed on the system, the bolts will break. There's going to be an automatic spring-loaded valve release on either side of these flanges, so that the loss of LNG is of minimal nature, and so you get this automatic breakaway and release, so that you're not damaging the hose, you're not creating damage to the vessel, and you're not damaging the tanker truck or the bunker barge. On each, there's one on each hose, the breakaway coupling on the receiving ship's manifold, and it ensures the hose does not break in case of marine movement or emergency. The coupling is the weakest part of the bunker hose connection by design. It's designed this way intentionally. On either side of that breakaway coupling are two quick closing shutoff valves. They close immediately upon breakaway, minimizing the amount of LNG trapped in the shutoff, minimizes the amount of liquid that's in the environment. That small amount of LNG, when it's in the ambient environment, immediately vaporize. In most cases, testing of these devices, the amount of LNG is so small that it never even has a chance to touch the ground or touch the surface below the breakaway coupling. It vaporizes so quickly, and it's of such a small quantity. Okay. This is a graphic of a breakaway coupling. Here is a breakaway coupling in its locked position or closed position. This is the flange connection right here, center. And as you can see, here is a valve face. The valves are in an open position, allowing the flow of liquid to pass through here unimpeded. If the coupling, and here the coupling is beginning to separate, as you can see. As soon as as these flange faces start working away from each other, the tension on the spring is released, and as you can see, the valve starts to close on either side of the flange. This is full open position, and here's the valve starting to close, spring-loaded. Just prior to the actual breakage of the bolts and the disconnection of the flange, you can see the valve seats are closed here. So in this little area right here, this small area where you're going to have an accumulation of liquid, when the actual break occurs, that liquid is going to immediately vaporize, and you can see a couple of parts, and the hose system separates. No damage done to the hose, no damage done to the connection on board the ship, and no damage done to the supplier's side. Excuse me. This particular design is from a company called Claw. As I mentioned earlier, we're not endorsing any manufacturers or whatnot. The information that was readily available to us, Claw is one of the companies that does manufacture type. There are other companies out there. Their designs are going to be similar, as in most cases, all a little bit different, so that patents aren't infringed upon, things of that nature. But they all serve the same purpose, and they all act in a similar manner. Your marine cryogenic breakaway couplings are designed to only release by inline pull. They are used between two strings hose. In other words, force is inline only. If you get a force in this direction, these bolts are not going to break. The force has to be a lateral force before these bolts will actually fail. The way this is the way they're designed. You can see this is a different type of spring-loaded valve arrangement. Another manufacturer, Mantech, but you can see that the end result is the same. When this flange is brought together, these 2 points of the valve stems, they press each other and force the valve into an open position so that flow is allowed to pass by. When the bolts break due to a lateral force being applied to the hose, spring forces the valve seat to closed position, so that and when the break occurs, it's just this little bit of space on each side here where you're going to have a small amount of liquid accumulated, and again, it's such a small amount when introduced into the environment, going to vaporize almost immediately. Obviously, you don't want to be standing next to one of these things, such as I'm not minimizing LNG. Any is an incident that has to be documented and explained. But it is such a small amount that usually it's not a problem. But you would not want to stand directly next to one of these things when it. Following slides are examples of how breakaway couplings are installed to protect the hose. All right, this is another type of breakaway coupling. See this this particular type unit, hose would be connected on this side, hose connected on this side. Here's your flange. Here's your flange face right here, and these are the weak bolts. Again, it's going to be a lateral force. It's going to be a force of direct pull that would cause these bolts to break. Bolts, once again, are designed to break at a lower force than is required to damage the hose. All right, here's the installation of one of these hoses, and rather than being in a vertical alignment, in this particular case, in a horizontal, this vertical alignment. Once again, you have a lateral force direction, or in this direction, force that would be required to fail. This particular one, here's the right here is the breakaway coupling. Flange on this end, a flange on this, which connects. There's one on a smaller supply line. This in all probability would be a nitrogen line, something like that for liquid nitrogen. But again, the concept is the same. Here's another one. This is a connection to a supply line. This, I suspect, is an oil line, MDO, MGO line. The function same. This is the brake couple right here. Force, the vessel moves away from the berth. Force applied in this direction. The failure is going to occur here. Valves inside on each side. These valves are going to close, and this breakaway could be conducted with a minimum amount of spillage, minimum and no damage to the hose. This is a cryogenic arrangement, as you can tell by the buildup of ice. Again, this is the breakaway coupling right here, and these are the bolts. So again, here's another, this is the Mantech system. These are probably for cryogenic use. They look like they're manufactured out of stainless steel. The actual breakaway couple right here, valves, spring-loaded valves, spring-loaded valve on this side of the flange, spring-loaded valve on the side of the flange. As you can see, they come in different sizes for different applications. Another means of connection, and these are the hard connections to the ship's manifold. Names are similar, so be sure you know the difference. We've just gone over the breakaway coupling, and then you have what are called dry disconnect coupling, dry break coupling, dry disconnect or dry break coupling. And this type of a coupling is for the actual connection hose manifold. They provide quick connect, quick disconnect capability, and they're designed for connecting the supplier and the receiver manifold. The dry disconnect coupling connects the hose to the manifold, and it's an automatic turn and lock mechanism. Has a built-in swivel, removes the hose twist and tension on the hose, and there's an automatic valve opening and closure that delivers non-spill efficiency. I'm going to send a link during the break. It's a animated graphic of how this particular valve functions, and it is a very, very good and very graphic depiction of the operation, and I'm sure you'll have a very clear understanding of how a dry disconnect coupling works. This is an example of a dry disconnect coupling valve. This is connected to the hose. This is a swivel right here, and you have these handles on each side of it. This portion of the breakaway coupling is connected to the manifold. There's a holding and locking device in here where this section is mated to the manifold, twisted in a clockwise direction. It's twisted in a clockwise direction. It locks onto the manifold, and simultaneously, the valve right here is pushed into the open position. This is another example. Rather than the handles on the side, it has a handle that encircles the full diameter of the connection. It's just a different type of design and how you connect. And as you can see, it's the same manufacturer. They just offer the option of different types of handle or control device on how the valve is twisted. Again, it's put in. Here's your locks that go into a mating surface on the manifold side, and when this valve is twisted, it locks into position. Valve base here is pushed into the open position. In the disconnection, when you turn this in a counterclockwise direction, valve automatically closes, and you just have a small space in here where there might be a little liquid that accumulated that vaporizes as the disconnect is made. Another manufacturer, again, similar type handles on the side. You can twist this, twist and lock, righty-tighty. You click this in a right hand in a clockwise direction. That closes and locks it. And when you want to disconnect, you come back into a counterclockwise position, turn to the left, and that creates the force for the disconnect. So the dry brake breakaway couplings are considered, they can be considered an emergency release coupling as well, but they do have to be manually operated. It's not an emergency release coupling in the sense that it operates automatically. That's what that's what the dry brake coupling is for. Dry brake coupling is emergency breakaways, emergency release coupling. That's the one with the bolts that are designed to break or force. So that is considered an emergency. The it releases the hose at an emergency occurs. Your dry disconnect couplers are for quick connect and disconnect only. They're not considered to be an emergency coupling. It's a manual valve. So you want something that's going to break automatically for it to be an emergency. Once again, to be clear, a dry brake or breakaway coupling, one with the bolts that are designed to break at a lower force than necessary to damage the breaker hose. The dry disconnect coupling for your quick connect and quick disconnect from the at the manifold wire. And okay. 10:30. We're looking at 10:13. Okay. That's going to be a wrap on this section, Jared. I'm going to send the link during the break, and the students hopefully will get a chance to see how these how the dry disconnect and or couplings work, and I think they'll find it to be perhaps a little bit clearer than my explanation. Very good graphic. So with your concurrence, we'll, I guess we can step into the break. What time would you like to come back?
How long is that video?
Oh, it's short. It's probably, it's only probably about 3 minutes.
Okay. Yeah, I think a break would be fine. We can take a half hour and then maybe we'll send the link out now and maybe they can watch the video quickly. And then
yeah, okay.
Should we come back at 11?
Okay, sounds good. I'll send that to you right now.
Okay, thank you.
Yep.
Yeah.